Alright, so today it's day 38. I'm gonna show what I did. So today was mostly about studying some really important concepts in machine learning and statistics. The first one was, for example, okay, I want to deeply understand variational inference, right? Because I'm reading about a paper about it. I already implemented like a paper about it, but I want to deeply, I know like the overview, the intuition, how does it work, but I want to understand the math. And in order to understand every aspect of it, I have to dissect it in smaller pieces and understand those smaller pieces. So one important aspect in variational inference is the Kuller-Levar divergence, and within this concept there is a concept of cross entropy. There is a relationship, and also there is the relationship with entropy. Okay, so let's start with that. The entropy is essentially the surprise, and I mean this is a very common concept. So it's basically how much information does how much information when an event happens gives to you, right? And it's also can be interpreted as surprise. If an event has lower probability, then you have lower surprise, or it gives you more information, the fact that it happens. Then you use logarithm to express it in bits, and that's it. And then when you compute that's the surprise, but when you compute the average expected value of surprise, then it's called entropy. All right, that's it. And then we have the concept which is cross entropy, which in essence compares okay, it says here when you believe when you believe the distribution is Q, but reality actually follows the distribution P. So the surprise when you assign the probability distribution Q, it's this, we know the formula, and the average value when the true value is P is gonna be this. And I mean it's pretty intuitive, right? And then we have the KL divergence, which is some sort of regret of using the wrong distribution, but in essence it compares two different distributions. It has like many interesting properties. For example, it's not a distance, like a distance comparison, so it's not symmetric. It's not the same comparing A and B distributions and B and A, right? And it's just one way in which we compare distributions, and it uses also entropy, right? So also I annotated the actual derivation of it, which this is the formula, and you can think about it. There's two ways of thinking about it, I believe. I mean, there are many ways. You can try to directly understand this formula, like this interpretation, or you can build it backwards, like saying, okay, I'm gonna define some sort of penalty of having like the true distribution, like the actual, okay, I'm gonna have like some sort of penalty. The penalty is gonna be 0 if it doesn't cost me anything to achieve like the target distribution, right? And the more it costs, the more penalty I have. So it's gonna be the difference between the actual cost minus the ideal cost. And this cost, we can understand it, it's essentially, we know, the cross entropy minus the entropy, right? And P is gonna be the true distribution, and Q it's the predicted one, right? And if we expand, I mean the entropy, we know the formula, it's gonna be the sum. We have, this is the cross entropy, we put P and Q here, and in the other one we put P in both sides. We can simplify, the sum it's in both sides, and P of X also appears in both sides. We factorize, and what else? This is different, right? Minus this and minus this, so we can put this minus this, right? We can multiply by negative, and this is gonna be yeah, because this is minus this, so this is positive, so we have P minus Q. All right, and then because rule of logarithms, if they are subtracting, you can divide, and this is the final formula of the KL divergence. And you can also actually interpret it as more, the KL divergence is the sum, no, the cross entropy is the sum of the KL divergence and the entropy. Okay, Now I'm gonna go a concrete example on like a specific problem in which we want to estimate a latent variable, right? It could be many things. That's the beauty of statistics. For example, you have like some data points and you want to estimate the center of the cluster, right? Or you have some sort of vehicle and you want to estimate how far are you like from a collision, right? So if you use like maximum likelihood, you estimate a single point, right? But I think sometimes, obviously, it's more useful to estimate directly probabilities. Because what happens if you like the highest probability value is a distance. It's some sort of distance, but actually the distribution has a high variance. Then you are not gonna be as sure that your prediction is right. So, and that's not the only time in which you want to estimate using probability distributions, right? Another one, it's simply because of computational costly. So we know that we can estimate like the parameters of the distributions using Bayes' theorem, right, with the prior and the marginal. And what would happen? We need in the denominator the marginal. So we know that that's like the integral. I mean, if it's continuous, that's the integral over all possible values that px can take. And if this is very huge, very large, this is impossible to calculate. So basically, we have to find another way in which we can estimate the shape of the posterior distribution and find the parameters that make the posterior distribution that minimize as much as possible the loss. That means that will be theoretically as close as possible as the real posterior distribution. All right, and this essentially, for some reason, translates to minimizing the KL divergence. It's not for some reason. I mean, it is minimizing the KL divergence because we are comparing two distributions, the actual posterior and our predicted posterior. So we want to minimize the KL divergence of these two distributions. What happens is that when you can expand, I mean, to do the KL divergence, we need the posterior, so it doesn't fix the things. But what we can do is that we can sort of make some math tricks, and we ended up with another value, which is actually called the elbow, which is this formula, right? So minimizing KL over these two distributions is mathematically equivalent to maximizing a quantity called elbow. All right, that's what is interesting, and this is like the main metric that we use for variational inference. I put also like some rule on how do we derive actually the elbow, right? Which is this. The right part of the KL is this, and we can express the right part as this. I mean, this is just substituting in the formula. Then if we use the Bayes rules inside the log, we can get this. Then yeah, this is this is the right side. We substitute this with this. This is this expanded. Okay, we separate the log terms, and then we ended up with this, right? Okay, we go this to the other side, and this is the elbow. All right, and I'm gonna give like just a specific example of variational inference. What could be an example? Okay, I think I'm not gonna give the example. I'm just gonna give like an intuition of the implementation. Basically, it will have two steps. The first step, it's called the M step, and the second more important step, it's called, where is it? Yeah, I skipped the first step. Okay, the first step is the E step, and the second step is the M step, essentially. And in the E step, you freeze. You freeze some parameters, and you estimate. For example, in this case, we have a concrete example with latent block models, because here you assume that you have like some sort of clusters, right? And these clusters change dynamically, but you don't know how do they change, like which. Okay, you can assume that they follow a Poisson distribution, and then you need to calculate, like for example, a parameter that assigns the probability that the data point, that a station belongs to the cluster, right? So you need to compute both of them, like the dynamically model of the cluster, like how it evolves through time, and the probability of belonging of each station to the cluster, right? And this is done by two steps. First, you fix one and you estimate it, and then you fix the other and you minimize the elbow, right? So in the second step, it's where we do the elbow. And then another important question is, how do we select what are going to be our latent, our variational, and our model parameters? And I put a table, which is this. And that's essentially it.